So when we work with the memory lane, the first question is, how do we find the vertex of a quadratic? And from last time, we know that the x-coordinate is found by using negative b over 2a. And then the y-coordinate we find by taking that and substituting it into our formula, which means that in general the vertex is negative b over 2a comma f of negative b over 2a. So that's what it looks like in function notation. Super ugly, but that's okay because we know we're just going to go find the x value and then substitute it in the function to get the y value back again. Now, how are profit, revenue, and cost related? If you just think in general for life, profit equals revenue plus cost. We can write that in function notation, and in function notation that's written as p of x equals r of x plus c of x. P of x equals r of x plus c of x. And then you're given some bit of information and you have to go and put the other pieces in there. And it's not plus, it's minus, sorry. Minus, revenue minus cost. Fix that, minus cost. What does it mean to find f of 2? Think for a second. Function notation f of 2. What is y when x is 2? So you're going to substitute it in and find the y value. Next one, number 4. Describe what it means to be an intercept. It just means when your curve hits the axis, whether it hits the x-axis or the y-axis. I'm not going to write that one down. The next one, find two functions who have a restricted domain and name that domain. Remember, domain can be restricted by fractions, so we could have a function that looks like this, whose domain is the set of all x such that x can't be 0, right? If we graph that guy, and I know you don't know this graph off the top of your head, and that's okay. It's down here in the bottom third quadrant, and up here in the upper right quadrant, it's a hyperbola. And for this guy, the range is the set of all y's such that y cannot be equal to 0. Sometimes you can only find the range by looking at the graph. So you can use your graphing calculator to be able to find that picture and then use the picture. And as you can see, this graph never hits this x-axis, and so it never becomes 0, which makes sense from up here because this fraction is never 0 because the denominator is where the variable is located. Now let's go ahead and find a different one. Ready? Let's let g of x equal the square root of x. So it's the square root function. Think, what do you remember about square roots and what's inside the square root? For domain, it's the set of all x so that x is greater than or equal to 0 because what's inside can't be negative. So when we find domain, we take what's inside and set it greater than or equal to 0. So let's look at the graph of this function, x and y. This one starts at the origin and comes over this way. This is g of x. What's this guy's range? Well, it does hit the point 0, 0, range or y values, right? And so his y values are 0 to positive infinity. Now, if you write that in interval notation, it looks like this. If you write it in set notation, It's the set of all y's such that y is greater than or equal to 0. So for the others, I use set notation. This one, we just wrote it both ways. These two guys mean the exact same thing. Ready? So this is really like a summary of our last few weeks together. How do you know if a function is increasing, decreasing, or constant? It is increasing when the y values are getting larger from left to right. I'm not going to write this in this tiny space. So when the y values are increasing from left to right, when the x values are continuing to go to left to right and the y values are going down or getting smaller, then it is decreasing. And as x goes left to right, if the y values are staying the same, then it's constant. If you remember, we did a number of graphs where we had to write down these intervals of increasing, decreasing, and constant. So it's that same idea. What I'd like to take a look at next is piecewise functions, and we haven't done this yet. And so I'd like to treat this from scratch and go ahead and graph this guy. And then after we graph it, then go ahead and answer the questions that are over there on the left. And so I'm just going to make mine larger and fit it on the side. You may have room on yours. When you look at a piecewise function first, the whole function is all three of these together. So that's the first thing to recognize, is that a piecewise function comes in pieces, and it has a different function for each part of its domain. So its domain is here. So let's go ahead and write that. This is telling you its domain. For this guy, it's telling you it's all x's less than -2, so negative infinity all the way to -2. And then the second line, it tells you we're going to use -2. And then the third line tells you everybody bigger than -2. And so that means we go from negative infinity to -2, include -2, and go everybody to positive infinity. That's really all real numbers, right? So this guy's domain is really all real numbers. Not all piecewise functions have all real numbers. Sometimes there's holes in them. Let's go ahead and take a look at this graph. I'm going to stretch it over here a little bit because we're working with -2 over on the left. And this first function, part of the function, is telling us that when x is less than -2, that's from negative infinity all the way over to -2, but not including -2, we're going to sketch y equals 2x plus 1. So we're going to make a little t-chart. And we're going to come up with 2 points. And with those 2 points, then we're going to graph this function 2x plus 1. But we're only going to graph it -2 and to the left. So let's use the endpoint -2. So when x is -2, we substitute it in. 2 times -2 is -4, plus 1 is -3. So that gives us the point -2, -3. Now we put a hole there because remember this function graphs all the way up to -2 but not including it. So we get a little hole. And then let's pick another point in that part of the domain which is less than -2. Let's not go too far. Let's use -3. So -3 substituted in. 2 times -3 is -6 plus 1 is -5. So that's down here further. So this graph of this line comes down in this direction, and it is y equals 2x plus 1. We just graphed the first portion of this piecewise function. The next line of the function here says if x is -2, y is 0. Well, that's not an interval. That's a single x value. So here at -2, the graph is going to jump up to to 0. So you're traveling the curve up this way from negative infinity, coming all the way up to x is negative 2, whole here, because we're going to not include that in this part of the function, and jump up and put a 0. Now we need to do this last line. Let's go ahead and do the last line. I'm going to move over a little so I have room. And this last guy is for x is greater than negative 2. So it goes from negative 2 forever over to infinity, and it's y equals x minus 1. Y equals x minus 1. Go take a look real quick, make sure I had the right equation. And we need 2 points to make a line. We're going to use that endpoint again, negative 2. Negative 2 minus 1 is negative 3. So that is this point right here, but we don't include it because we're not including the endpoint. Then we need another point in that interval. So let's go ahead and pick something else in this interval here. Let's pick 0 because we love to know where we hit the axes. 0 minus 1 is negative 1. So it's here at negative 1. That means this guy comes in this direction, and we label it y equals x minus 1. Now obviously mine is not to scale because it should be a little bit more slanty with the red line than it is with the blue line. And so my scale is off for sure. We have graphed one portion of the piecewise over here, another piece where it jumps here, and then the other piece here. Notice none of them overlap. Here we have open circles where those two pieces seem to overlap, but they don't include that endpoint, so they don't really overlap. Sometimes they give you a point that actually fills this in, but you do need to go one at a time. I highly recommend you do T-charts, you do left to right. Do the first line, the next line, the last line, and graph them one at a time. And that way then you get this cohesive whole for the piecewise function. Now let's go answer the questions that they're asking us over here on the left. And the first question they ask us is find f of negative 2. Remember, when we see that notation, that's the question that they're asking you is what is the y value when x is negative 2? So come over here to the domain. Where is negative 2? Negative 2 is sitting here. So what's y? 0. So f of negative 2 is 0. What is f of 1? What is the y value when x is 1? That's the words that go along with the notation. What is the y value when x is 1? Come over here, look in the domain. Which domain has 1 in it? Not the first one, not the middle one. The bottom one does. That means we use this function. So we substitute a 1 in for x. 1 minus 1 is 0. And so f of 1 is equal to 0. We already found the domain of f before we graphed it. So the domain is all real numbers. We graphed it. Use the graph to find the range. Now we look at the graph. The range, remember, is all y values. So you start down here. And what do we get for y values? So I'm going to scoot it over and make it a little bigger so I can use a different color. And it goes from down here, negative infinity. It comes all the way up here to, wasn't this a negative 3? And at negative 3 there was a hole. Do you remember there being a hole at negative 3? That's the endpoint where they match. And then the y values go forever up to positive infinity. So for us, the y values go from negative infinity to negative 3, but don't include negative 3. And then go from negative 3 to infinity. We have to write that in interval notation. So let's go back over in that space and write that in that notation. So it is negative infinity to negative 3. I'm going to run out of room anyway. Union negative 3 to infinity. Round parentheses on the negative 3's because they don't include that value. Parentheses on the infinities because we can never be infinity. And so that is the new information for the piecewise function.